Hello and welcome to this PIR Live Event webinar. My name is Ben Hobbs and I will be your host today. Just a reminder for those classrooms joining us live, if this is your first time joining us, we are moving away from the Q&A, or moving away from the chat, sorry, and moving towards the Q&A function. So I'll ask you to direct your questions there when we move into the Q&A section of the webinar. And you can also prioritize questions that you see that you would like answered by thumbsing them up in the Q&A section. So without further ado, I would like to introduce our guest today, Dr. Michael Reid. Dr. Reid is an associate professor at the University of Toronto, and he is also the outreach coordinator at the Dunlap Institute for Astrophysics and Astronomy. Thanks for joining us, Dr. Reid.
Hi everybody.
So I'll let you take it from here.
Great, so thanks everybody for coming. I look forward to answering everyone's questions. Just to sort of stimulate the discussion, I'm going to share with you some of the interesting research that's being done these days on the search for planets and for life elsewhere in the universe. So as introduced, my name is Michael Reid, and I'm a professor of astronomy at the University of Toronto, where people research all sorts of different aspects of astronomy. But one of the main things that astronomers are interested in these days is looking for places in the universe where there may be conditions similar to the ones that we enjoy at home. So I'm going to walk you through some of the ways that we do that and some of the exciting results. So hopefully everyone is familiar with this object. This is our home planet Earth, and most of your day-to-day experience is concerned with this object, right? You walk around on the surface of the Earth, all of your food comes from the Earth, all of your family lives on the Earth, all of our experiences are confined to the Earth. But as astronomers, our task is to sort of flip that perspective around and look away from the Earth and think about the vast rest of the cosmos. So one picture that I think does a really good job of contextualizing, of helping you understand how astronomers see the cosmos, the universe, is this one. So this is a very, very special picture. This is something we call the Hubble Deep Field. It's a picture taken with the Hubble Space Telescope, one of the most sensitive telescopes we have. And to take this picture, what they did was point to a blank part of sky, a part of the sky that didn't seem to have anything in it, and leave the shutter open on the telescope for days and days and days to gather as much light as they could. To give you a sense of what you're seeing, almost none of the points of light in that picture, just a couple of them, are stars. The vast majority of the thousands and thousands of points of light in that picture are galaxies. Those galaxies, each one of them contains billions, or in some cases, trillions of stars. That's a lot of stars. So a billion is 1,000, 1,000, 1,000. And a trillion is 1,000, 1,000, 1,000, 1,000. It's a really big number. Each of the little points of light that you see in this image contains that many stars. And there are thousands and thousands of those points of light. To give you a sense of how big this image is, if you were to hold your pinky finger out at arm's length, this part of the sky that you're seeing in the picture covers about the same area as your pinky fingernail. And the whole sky looks like this in every direction that we look. There are thousands, millions, billions of galaxies, each of which contains billions, trillions of stars. It's an almost unimaginable number of stars. And when we as astronomers look at the universe this way, we start to think, wouldn't it be really strange if all of those almost uncountable numbers of stars had no planets? That would be really weird, right? If the sun, our own star, had all these lovely planets orbiting it, and then no other planets existed anywhere. But for a long time, thousands of years, we couldn't answer that question. Because, as it turns out, it's really hard to find planets orbiting other stars, even near to the sun, even in our own part of the universe. And there's a really simple reason for why that is. So let me give you an analogy. Here's a picture of a car with its headlights on. So if you were to try and take a picture of a planet orbiting another star, that's like trying to take a picture of a firefly, a tiny little bug emitting just a tiny, tiny little bit of light, sitting on top of the headlight of this car. There could be 100, 1,000 fireflies on that headlight, but because the headlight itself is so very bright, you can't see them. And this is what happens when we try and take pictures of planets orbiting other stars. What we see is the brilliant glare of the star, and it washes out the light from the planets. So it makes it very, very difficult. And that's why for thousands of years, people wondered about this question, but couldn't answer it. So relatively recently, in the last 20 years or so, we have started to develop ways of indirectly figuring out that there are planets orbiting these stars. And I'll show you the easiest way. There's actually a really simple to imagine way. It's a little bit complicated to actually do, but it's really easy to understand. So what you do is you stare at a star, any star you like, and you wait. That's all you do. You stare and wait, and you take pictures for year after year after year while you stare. And if that star has a planet orbiting it, as the one in this animation does, then when that planet passes in front of the star, it will block a tiny little bit of the light from the star. So here that's about to happen. Here goes the planet across the star. When the planet passes across the star, it blocks some of the light from the star. And if that happens over and over and over again, then you can work out that what is happening there is there's a planet orbiting the star, the planet blocks the light, and that's why the star dims every so often. So if you imagine aliens staring at the sun, then if they watch the sun very, very closely for a long time, every so often one of the planets of our solar system, Jupiter or Earth or whatever, will pass in front of the sun, it will block light from the sun, and they will say, aha, even though we can't actually see Earth or Jupiter because the sun is too bright, we can tell that they are there because they block some of the light from the sun. So this technique has been very, very successful now. We've been using this for 20 years. There's been a dedicated space telescope designed to do just this. It stared at one patch of the sky for years on end and just watched the stars to see if any of them had these little dims. And in fact, they did. Thousands and thousands of them did. So we have now been able to find many, many planets orbiting other stars. Here's just one example of the kinds of solar systems that we have found. So remember, a solar system is a star and the planets that orbit that star. So in our solar system, we have the sun and the 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But in these other solar systems diagrammed here, you see a star at the center. And if you look at the big one in the middle, Kepler 452, it's called, there is a planet. We call it Kepler 452b because we haven't had time to give all the planets sort of nice names. And that planet is somewhat similar to Earth. It's bigger, but we believe it's rocky like the Earth instead of a gas planet like Jupiter or Saturn. It's a rocky planet, and the green area in the diagram is showing you what we call the habitable zone, or you may hear it called the Goldilocks zone. That's the distance you have to be from that star if you want to be neither too hot, because you're too close to the star, or too cold, because you're too far from the star. So this planet, Kepler 452b, is in that range where the temperature is just right. Just like think of the story of Goldilocks and the 3 bears. The one bowl of porridge is too hot, one is too cold, and one is just right. So in this Goldilocks zone, that's where you can put a planet, and it can have a good temperature to support an environment like the one we have on Earth. And in fact, we have found many star systems like this, where there's a star with a planet at just the right distance from the star to maybe be able to support life on that planet. But we found lots and lots of these planets now. This is a little bit of a complicated diagram, but what it's showing you is different types of stars going up on the vertical part of the diagram. So there are cooler, redder stars at the bottom and hotter, whiter stars at the top. And then how much energy, how much heat those planets are receiving from those stars. And again, the big green band through the middle of the diagram shows you the parts of those solar systems where you could put a planet and it could be like Earth. So what this is showing you is that we've now found dozens of planets orbiting other stars. Each one is represented by a yellow or a blue circle. Dozens of planets orbiting other stars that are at about the right distance to potentially support an environment like the one we have on Earth. So that's wonderful news. You may have heard of this one in particular, the one on the top here. So on the bottom is a representation of our own solar system. The sun is at the center. Then we have Mercury, that's too hot, so it's colored red. Venus and Earth are in sort of the green zone or close to the green zone, and then Mars is edging out towards the blue zone. But there's another nearby solar system. It's not that far away from our own solar system. It has, we don't even know how many planets, but so far we know of 7 planets in that solar system, and 3 of them, we call them E, F, and G, because again, we haven't given them all nice names yet. E, F, and G are all in that Goldilocks zone. So this makes astronomers very excited about the possibility of finding planets elsewhere in the universe that could support life. However, there's something funny about those planets. It happens that in a lot of these solar systems, the planets that we find are what we sometimes call eyeball planets, and I'm showing you one of those here. So on an eyeball planet, what's happening is that one side of the planet always faces the star. So you have, unlike Earth, where the Earth spins around on its axis once every day, and so every part of it gets warm during the day and then cools down at night, and it stays sort of even temperature. On these eyeball planets, one part of the planet stares at the sun all the time, and the other one always faces away. So that could mean that on the night side, it's permanently night, and it would be very cold there. You can see some ice in this diagram around the night side. And on the day side, it's permanently day, and it's therefore very warm there. So that could pose some challenges for these planets supporting the kinds of environments where life could exist, because it would be very hot on one side, very cold on the other side. But it might mean that around the middle of the planet, in the day-night dividing line, sort of where twilight is, you could have a whole set of environments that could be good for life. So that's kind of a bit of a downside. You know, these planets are probably quite different from Earth, but they may still support life-supporting environments. So the future of this kind of science is through a couple of different space telescopes. So there's a brand new telescope, just went up last year, called TESS. TESS has a special job. What it's going to do is apply this technique that I described of watching stars and waiting for them to dim if they have planets orbiting them. Instead of doing what the telescope I described earlier did, what that one did was it stared at one patch of sky, and it looked at all the stars in that patch of sky. What TESS is going to do is look all over the sky, not just one patch, but the whole sky. And it's going to look at all the nearby bright stars and check all of them for planets. So that should increase the number of solar systems we know about that are close to us and that may be easier to study than the ones that are very, very, very far away. And then what we will do with those is use this telescope. This is a new telescope called James Webb Space Telescope, and it hasn't launched yet, but it will launch probably in a year or two. And what you can see in the diagram here, it's a very complicated, or in the movie, it's a very complicated telescope. It has to go out in space. It's got all these robotic bits and pieces that have to unpack it. It has to be very small, squeezed together when it gets launched from a rocket from Earth. But then for it to do its job, it has to get much bigger when it's in space. So it has to unfurl this sun shield, that's what you're seeing there, the silver part. And then the gold part in the middle is the mirror that the telescope uses to gather light. And this is a very big telescope. That mirror is about the size of your classroom, a little bit bigger. And with a telescope that size, you can gather a whole lot of light, and it also has some special technologies built into it to block the light from the stars and only allow us to see the light from the planets orbiting those stars. When we are able to do that, it will tell us more about what those planets are actually like. Do they have, for example, water on the surface? Do they have air that we can breathe? Would they maybe be places that it would be good for people like you to go someday if we develop the ability to travel such long distances? So that, very briefly, is a quick introduction to our current search for planets outside the solar system. We have found lots of these planets. We're going to find thousands, millions more in the coming years, and we hope very soon to be able to tell you a lot more about each of those planets individually. So I will stop there and take some questions.
Thank you, Dr. Reid. Just before we move into the Q&A, I would like to remind the classrooms joining us that if you see a question that you would also like answered, you can prioritize that by clicking the thumbs up icon just below the question, and I will relay these to our host. So why don't we get started with a question from Ryan from Midnapore School, and he is wondering if anyone has found air on a planet like Earth, air that's like the air we breathe on Earth here.
Yeah, air. So there is some amount of atmosphere, some gases on most planets, not all, but most, but none of the ones we've found so far are like Earth. So to give you an example, the planet Venus in our own solar system, it's pretty much a twin of Earth. It's the same size, the same mass, very, very similar. But the big thing that differs is the atmosphere. So on Earth, our atmosphere is made mainly of a chemical called nitrogen. But on Venus, the atmosphere is made mainly of a chemical called carbon dioxide. And that chemical is really good at trapping heat, and it creates terrible problems, makes it very, very hot on Venus. So even though Venus is otherwise a twin of Earth, its atmosphere is very different, and that makes a big difference. We've never found planets beyond our own solar system whose atmosphere we can study well enough to be able to say what it's like. And that's part of what this James Webb Space Telescope is meant to do.
Thank you. Could I just get you to stop sharing your screen before we move to the next question? Thank you. So the next question comes from Mr. McCabe's class, and they would like to know, why did we start looking for exoplanets?
Why did we start looking for them? Because it's exciting. That's the basic reason that, you know, humans are explorers, and we like to know new things. And we have literally been wondering since as long back as anyone can remember, thousands and thousands of years, people have wondered, you know, are we alone in this universe? Are all these thousands, millions, billions of stars really just devoid of life? Are they just lifeless rocks? And so it's curiosity that makes us want to know these things. That's the main reason.
Very interesting. Our next question today is from Mr. Samble's class, and they would like to know, when can we live on Mars?
When can we live on Mars? You know, that is almost entirely up to you. We don't have, there's not a lot that's stopping us from going to Mars, except that we need to want to do it. The technologies that we need are mostly in place, not everything, but we could live on Mars in the relatively near future. What we need is people who are willing to spend the money and the time and the effort and the resources to actually get us there. So if you're interested in that, I would say, you know, think about a career in engineering or in medicine or one of the many fields that will be useful to help us get to Mars.
I'm getting this next question from quite a few classrooms. Seems to be an interesting one. To date, have we found any evidence of life elsewhere in the universe?
Have we found any evidence of life? So we have found little kind of hints here and there, but nothing certain. So for example, there's a rock that was blasted off Mars a long time ago by an asteroid, and it fell to Earth. And that rock has little things in it that look maybe like they could have been fossilized bacteria that once lived on Mars, but a lot of people say that they probably aren't. Just very recently, there was an object that came into our solar system from outside, sort of a big kind of a rocky thing as far as we can tell. And it's the first time we've ever seen an object enter our solar system from elsewhere in the universe. And people have been looking at it very carefully because although it's extremely likely that it's just a rock, you never know, right? Maybe it's something else. Maybe it's an artificial device that someone has sent to make contact with us. As far as we can tell, it's not, but people keep looking. So no clear evidence yet, but we're very actively working on that problem. There are plans to go and explore the moons of Jupiter and Saturn, which are places we think would probably be good for finding life and things we could probably do in the next 10 or 20 years.
So this question maybe feeds off this one a little bit. This comes from Sophie. She's in grade 6-7 at St. Nicholas. And she says, since there was a discovery of water on Mars, is this maybe evidence suggesting there was organisms living there in the past?
Yeah, so we've known since at least the 1970s, a long time ago, that there was some kind of water on Mars, but for a long time we thought it was all frozen. In the last few years, we've started to see some tantalizing evidence that maybe not all of that water is frozen. Maybe some of it is still liquid, and it may remain liquid for long periods of time. We're not completely sure about that, but it's looking reasonably positive. So if that's true, if there is liquid water on Mars, that raises our hopes that there may be something living in that water, because we know that whenever we find liquid water on Earth, there's almost always something alive in it. However, something that's even more hopeful is we know for sure that a long time ago, billions of years ago, there were oceans on Mars. And so perhaps life developed in those oceans and is surviving in tiny, tiny little bits of water here and there on Mars, but we've yet to confirm that.
Interesting. So our next question comes from Miss Ferry's class, and she would like to know, how do we name these new planets that we're discovering?
How do we name the new planets? So astronomers have a real problem with naming things because we discover so many things that it would take our whole life to name them all, right? So for stars, we just give them kind of catalog names. You saw with the Kepler Space Telescope, this one that was searching for planets for a long time, the way we named the stars was just with a number. So we would say the first star that Kepler looked at was Kepler 1, the second one, Kepler 2, and on and on and on. And then we consider the star to be letter A in that solar system. And then we put letters to the planet. So the first planet we find is B, the second one is C, D, E, F. So that's why these planets that we find wind up with names like Kepler 1218c, something like that. However, very recently, because those aren't very satisfying names, they're hard to remember and they're hard to say, we have actually started naming them, giving them proper names. And the way we do that is actually we let you name them. So there's a body in the world called the International Astronomical Union that records the names for all of the things we find in space. And they run contests every few years to allow people to suggest names for these new planets that we have found. And I think now about 50 of them have been given names, often by school kids from around the world.
Interesting. So now that we're going out and finding these planets, Ms. Falconer's class is wondering, what are scientists proposing for methods of traveling to these new solar systems?
Yeah, so to travel to another solar system is currently not something we can do, not with people. There are people who are trying very hard to come up with a way to send tiny, tiny, tiny robots just to the very nearest star. But even that is tricky and would take probably about 10 years for those robots to get there. So for right now, actually traveling to other solar systems and landing on these planets is something we don't know how we would do. It would take thousands, maybe millions of years to send a human there, and that's obviously way too long. So we have to work on new technologies, new ways of thinking about this problem, and that's something that will probably be up to you guys to think about. Figure out a new way to get us to the next star over so we can see these planets up close.
So this is sort of a two-part question that is somewhat related to that. Hari from in 5th grade at Eden Rose Public School is wondering, firstly, what is a black hole? And secondly, could they be used to travel to different solar systems? Okay,
black holes. So that's a different thing. But what is a black hole? Basically, what a black hole is some object, usually a star, that has collapsed under its own gravity until it is really, really, really packed together, really dense, right? So you may start with a big star and the star dies, it blows up, and the explosion makes the core get very small, very dense. And what happens then is that the gravity of that object gets really strong, and in order to get away from it, you would have to be going faster than the speed of light, which isn't possible. So that object winds up basically becoming a kind of a hole. It's a thing that you can fall into, but you can never get back out of. And so that's why we call it a black hole. Light can't get out, nothing can get out. So what was the other part of the question there? That was...
So the other part of the question was asking, could we potentially use these as a method to travel?
Right. Could we use them? Probably not, but we don't understand enough about them yet. There's some very deep problems in science with trying to understand what's going on inside black holes. We know that the laws of science, laws of physics as we understand them, don't work properly for the centers of black holes. So to figure out whether there's anything you could ever actually kind of use them for is a little bit beyond us at this point.
Interesting. So this question is referring to the James Webb Telescope. And Jolene is wondering, how long did it take to create the telescope? And how big was the team of people that really put it together? And when will it start looking for new exoplanets?
So how long did it take to create it? A very long time. They've been building it already for probably about 10 years, just actually putting it all together and developing all the technologies that are needed to make something like that. And they've been planning to build it for probably about 30 years now. It's been a really long time. That's how space telescopes work. They're very complicated. They take a lot of money and a lot of time and a lot of people. So you asked about the people. There are definitely thousands of people, maybe tens of thousands of people who have contributed bits and pieces to that telescope. And it takes a long time and a lot of people to do it, and we pin all our hopes to it, and we really hope it works.
Mm-hmm. I imagine quite a few dollars as well.
Quite a few dollars, yeah, billions of dollars, yeah.
So this next question comes from Miss Spooner's classroom. And she would like to know, how many solar systems are there out there?
How many solar systems? Well, that's a question we've been struggling with for a long time. So I mentioned that there are, so many planets, stars rather, trillions and trillions of stars. Now we're starting to get a handle on how many of those stars have planets, and it seems that it's almost all of them. We very rarely look at a star and see no evidence at all of planets. So it seems like the fraction of stars that have planets is close to 100%. Probably not 100%, but close to it, which is really positive in terms of the search for places to find life in the universe, because it just greatly, greatly multiplies the number of possible places.
Mm-hmm. So what are the chances that humanity gets to any exoplanet, let's say, within the next 100 years?
Chances of getting to an exoplanet in 100 years, again, that's one of the things that depends entirely on, people who are in grade 6 right now, because you're going to be the ones who will develop the technologies that will allow us to do that. Right now, we don't have any way of doing that. The kind of propulsion systems we use for rockets now are chemical rockets, right? So when we want to go to the moon, when people used to do that, we haven't done that in a long time, but when we used to do that, we used chemical rockets. You put a bunch of fuel in a rocket, you basically light it on fire, and you rocket off to the moon. But a rocket like that would take many thousands of years to get to even the nearest exoplanet, the nearest planet orbiting another star. So to get there in a shorter time, maybe in a human lifetime would be nice, we're going to need some completely different way of traveling that no one has invented yet. So it's going to be up to you guys to invent some of that.
Mr. Babcock's class is wondering, firstly, how are planets created? And the second part of that question is, could we make artificial planets?
How are planets created? Planets are created when stars form. So a star forms from the collapse of a big ball of gas and dust in space. Space is full of bits of gas and dust, and sometimes they draw together and they start to collapse. The gravity of all of that stuff, all that gas and dust, crushes it. Most of the stuff becomes a star, but some of it doesn't manage to make it into the star, and those bits and pieces become planets. Could we make one artificially? This is a very, very interesting question. So currently, no, this is well beyond us. But one of the things we look for, because of course, while we're looking for planets, we also want to know, is there life on any of those planets? That's a really interesting question. And it's hard to figure that out because we can't see much detail on these planets. We can barely see them at all. So one of the things we look for is, has anyone else out there made a planet? And you can imagine if you made a planet and you wanted to make sure that somebody looking at that planet from extremely far away would know that someone had made that it wasn't naturally occurring, that it took technology to make it. What you might do is make it a really weird shape. You know, planets are round, all planets are round. So if you wanted to make a planet and make it clear to anyone who spotted that planet that it was artificial, you would potentially make it a pyramid, make it a cube, make it some other shape. So when we're looking for planets orbiting other stars, we always check, just in case. I mean, we don't expect it, but just in case, we check, you know, is this planet some funny shape that maybe somebody made it deliberately? We can't do that, but maybe somebody else can.
So this next question from Ms. Baggio's class, maybe not particularly directed at you, but scientists in general, and they are wondering, do you share your work with, share your discoveries with other countries?
Yeah, so astronomy is actually an international science. We just talked about the James Webb Space Telescope. It's a very expensive thing to build. It costs billions of dollars. And most countries can't afford that on their own. Certainly Canada cannot afford to build something like that on its own. It's way too expensive. So astronomy is very international. We collaborate among almost all of the countries on Earth. The James Webb Space Telescope is being funded and built by people from North America, South America, Europe, Asia, Australia. It's very, very international. And as a result, when we get pictures from telescopes like that, we share them. So they go on the internet and they become freely available for anyone in the world to look at after the astronomers have had a couple of months to kind of look at them themselves and make their discoveries. They just get put on the internet and anyone can look at them.
Well, I imagine that certainly helps push science forward, the fact that everyone is communicating. We're just running out of time here, so if I could ask you one last question. Do you have any advice for students that are watching today that are maybe considering pursuing a career in astronomy or astrophysics?
Yeah, so the usual way that people go into astronomy, if you want to become an astronomer, usually what you do is make sure all through your school that you take lots of science and math classes, okay? And I know that sometimes when people take science and math, they think, I don't know if this is all that interesting. You know, maybe it's a little bit difficult. You don't get the astronomy until later on, but trust me, stick with it. Take science, take math. When you get to high school, take all your physics, your chemistry, your biology, all the different kinds of sciences. And then when you get to university someday, you can do a degree in astronomy, you can do a degree in math, in computer science. There's a lot of different routes to ultimately becoming an astronomer and a lot of different kinds of specializations that different astronomers have. So there's lots of ways to become an astronomer, but the important thing is early on you have to remember to study lots of science and math.
Well, that's all the time we have for today, but thank you, Dr. Reid, for giving us some perspective of really where we fit into our place in the universe. So next week on PIR Live Event, we're going to be looking a bit closer to home as we dive into the human microbiome with Dr. Emma Allen Verco. More information about these webinars and other PIR educational programs are available at pirweb.org. Thanks for tuning in and have a wonderful day.